Here are some quick notes on the Eddington gray atmosphere to accompany Chapter 3 of To Build a Star. So the Eddington gray atmosphere is what we're commonly going to use because it enables analytic solutions to stellar problems, and that's important because it lets you get a feel for basically how certain problems scale, what order of magnitude you should get for a solution, and it's also just something that you can actually do by hand, so it's a good way to check a code, for instance. So the assumptions are, gray just means that the opacity is frequency independent. Okay, we know that this is not a great idea. You saw previously that the opacity does change as a function of frequency, especially bound-bound opacities, right? You have big spikes, or big changes in the opacity at certain frequencies. Another assumption is local thermodynamic equilibrium. So this just means that the environment is thermalized. Okay. Of course, this can't be totally true. At an optical depth of roughly 1, the photons aren't thermalizing, right? To thermalize, you need many scattering events. At optical depth of 1, you by definition only have around 1. So nonetheless, we're going to press on. And then a final assumption here is the Eddington approximation. So this assumes that your intensity is linear in cosine of theta. So when you represent the intensity distribution in terms of Legendre polynomials, you just keep the linear terms in cosine of theta, which basically just means you don't have a really high order anisotropy. You don't have a really fancy shape. Though, of course, at an optical depth of around 1, your photons aren't going to have lots of scattering that are going to ensure an isotropic distribution. So this doesn't sound particularly realistic. This isn't looking very good. How good of a job does the Eddington gray atmosphere do? Let's just look at two or a few different examples. Okay, so let's look at the radial temperature dependence of our star. So the Eddington approximation for a gray atmosphere yields something like this. So you have that your temperature at a given optical depth is proportional to the effective temperature. Right? So it's really temperature to the fourth, effective temperature to the fourth, but you have a kind of linear temperature dependence with depth, or temperature to the fourth dependence with depth. So what would the core temperature be for this if this were true? So from our quick notes on photon diffusion, we have that the average mean free path is about 0.1 centimeters. If you do the constant density model, you get something that's more like 1 centimeter. So not that different of an answer. So using this average mean free path, then the optical depth to the core is just the radius of the sun divided by that average mean free path. Plug in the order of magnitude numbers, and you get something like 7 times 10 to the 11 mean free paths. And you'd get something like 10 to the 10 with the constant density model. So keeping in mind that we can measure the effective temperature to the sun, let's just round to 5800 Kelvin. Then the core temperature would be around 5 megakelvin, according to this Eddington approximation here with our gray atmosphere. So let's just compare that to the real value. You have 15 megakelvin is actually around the central temperature of the sun, and in our constant density estimate, you get around 6 megakelvin. So this isn't too shabby, right? It's the right order of magnitude. So it means, okay, this is one piece of evidence. This isn't too bad of an approximation. Another thing we can look at is that at an optical depth of 0, the ratio of the temperature to the effective temperature in our Eddington gray atmosphere approximation is 1 over the 4th root of 2. And so that's 0.841. If you don't make this Eddington approximation, which is the linearization in of intensity in terms of cosine of theta, then the gray result that you get is more like the 4th root of the square root of 3 over 4, so 0.811. So both of these are gray atmosphere approximations, but one includes the Eddington approximation, and you can see that at least taking the Eddington approximation isn't that bad. I mean, we're talking like 10%, not too bad. And then one more thing that we can look at with the radial temperature dependence is that we're saying here with this approximation that the temperature dependence with the optical depth is actually pretty weak, right? So temperature doesn't change that rapidly as a function of depth. So remember when we looked at the quick notes on star formation, we said that the temperature was roughly constant in the photosphere, and that's what you need in order to have your Hayashi track to be roughly vertical. Well, we know the Hayashi track is roughly vertical, and so the temperature of the photosphere needs to be roughly constant, and indeed that this formula gives us that. So just some evidence that the Gray-Eddington atmosphere approximation isn't too bad. This is a phenomenon known as limb darkening for stars. So what we're going to do is let's make an approximation that our atmosphere is plane parallel. So we're looking just right near the surface, roughly 1 optical depth. Okay, so our atmosphere is a very thin slab. So if we view this from an angle, so if we view it face on, then the optical depth is just tau, and that's typically how we refer to a radial coordinate as optical depth of tau. If we view it from an angle, then we have some effective optical depth, right? You go through a bit more of this plane parallel atmosphere than you would if you were viewing it strictly perpendicularly to the plane. So with our drawing here, with the angle defined as such, then you can get a relationship between your optical depth when you're perpendicular to the atmosphere versus the effective optical depth viewed at some angle. And we find that the depth that you're looking at that corresponds to some effective optical depth is the effective optical depth times cosine of theta. Now, by definition, we're seeing light coming from an effective optical depth of around 1, right? So once your optical depth is greater than 1, then the photon's going to scatter, okay? And it's going to scatter or be absorbed, and so then you're actually going to be viewing a photon, if it's a scattering event or an absorption and re-emission, from a shallower depth, okay? So by definition, we're viewing effective optical depths around 1, so that means that our optical depth is something like cosine of theta for our plane parallel photosphere approximation. So tau is equal to mu. So remember, we use mu as shorthand for cosine of theta. Okay. So then we can take in the book, there's a very nice derivation of the intensity as a function of optical depth, and we can then, well, the intensity is a function of optical depth, right? You have 3/4 pi, Stefan-Boltzmann constant, effective temperature to the 4th, times 2/3 plus should be tau. We're then plugging in the cosine of theta, or mu, for the optical depth because of this plane parallel approximation we just came up with over here. So then our intensity at any given angle, or viewing angle, cosine of theta, we now have the black body flux that you recognize here, times 3/4 pi, times 2/3 plus mu. Okay, so what does that predict then, right? This is the intensity given some viewing angle. So we can then look at the ratio of the intensity when you view it head-on to the intensity when you view it some angle. So that's then 3/5 times 2/3 plus mu, basic cosine of the angle that you're viewing from. So if we're viewing our star or our photosphere face on, then this is 1. Right? So if we're viewing from straight above, then the intensity is defined as 1 here. And if we're viewing at cosine of theta is equal to 0, so basically right along the edge here, viewing from the side, then we find that the intensity relative to the central intensity is 0.4. Okay, so let's confront this with data. This is the ratio of the intensity. So intensity viewed head-on is I naught, and then at some angle is I, so I over I naught is what we're looking at, as a function of cosine of theta. So when we're viewing straight on, this agrees pretty well with this data. So this is from a paper that I found from the 80s. These purple points are the measurements. They agree pretty well. As you get to more extreme viewing angles, there's some divergence, but nonetheless, where the data ends, you have something in the, let's say, 0.38 around there, whereas in reality it's more like 0.45. Not terribly bad, right? Tens of percent, but still the prediction is relatively close. And what this limb darkening is then is when you look at the sun, you see it's getting dimmer as you get to the edge. and that's because you're looking at shallower and shallower optical depths. The intensity is dropping. So that's the phenomenon of limb darkening, and it's understood, I'd say, pretty well for this plane parallel approximation using the Eddington gray atmosphere. And just as a final point, it's very interesting, how do you measure this limb darkening? You actually do it with transits. So the transit of a planet in front of a star, so in this case we're talking about the sun, but you can do this for any planet. When you have a transit of a planet in front of the sun, or in front of any star, sorry, you basically look at the intensity of light as that planet goes over the edge here, and you know pretty precisely when the planet is at a given location because of Kepler's laws, and you can then basically analyze how that intensity changes when the planet's transiting. And that is how you can measure this limb darkening, and that is also one way that you investigate the atmospheres of both host stars and planets as well, is using these transit events, which is kind of an interesting aside. So the upshot here is that the Eddington gray atmosphere is pretty okay, right? It does a pretty good job. It's not going to knock your socks off, but it's a pretty good estimate at least, and a good way to check a code if you're going to do something fancier. And that is it for these quick notes on the Eddington gray atmosphere.